While we were doing this reaction, that is the free radical halogenation of methane, there we can have a specific question. That is, what would be the condition to obtain CH3Cl as the major product? And the option that could be given would be like the first that it could be CH4 excess plus Cl2 in presence of heat or light. The second condition could be CH4 plus Cl2 giving us heat or light. Here, when we say that CH4 plus Cl2, then in that case, it means that CH4 and Cl2 are in proportionate amount, that is similar amounts. Now, the third option could be that CH4 limited while Cl2 in excess with heat or light. And the fourth option could be that any of these. You need to understand that if we have CH4 in excess, then in that case, CH3Cl would be the major product. That is, we have CH4 in a huge excess and chlorine in a limited amount. That would mean that chlorine is going to attack on CH4 in a much lesser amount, since it happens to be less. While if you use the third option where Cl2 is in excess, then in that case, CCl4 would be the major product. So we can actually set the condition of the reaction in such a manner that we can get one of these two products as excess. We need to understand again that CH2Cl2 and CHCl3 will not be obtained in excess in whatever condition we create. If we keep them equal, then in that case, we are going to end up with a mixture of all the four. If we have one thing in a little excess, then in that case, again, we are going to get a mixture only. So this reaction can be used to obtain excess of CH3Cl, or it can be used to obtain excess of CCl4, but it cannot be used to obtain CH2Cl2 or CHCl3. So that was a slight reaction. And now we are going to talk about the reactions of alkene, which give us the alkyl halide. So we have the reactions of alkenes to give haloalkanes. Now, we talk about the alkenes. Now, we can have a specific kind of an alkene, like we have C double bond C. Here we have another C, and here we have a position. Then we could even have the benzene ring, and we could have this position. Now, let's talk about the position in an alkene. Considering this particular position, that is, the group attached to the carbon containing the double bond. This particular position is called the vinylic position. If the hydrogen is attached to this particular position, it's going to be called the vinylic hydrogen. If OH is attached to this position, this is called vinyl alcohol. If halogen is attached to this particular position, it's called vinyl halide. On the other hand, this particular position is called allylic position. The allylic position, like if we have hydrogen here, we are going to call it allylic hydrogen. If OH is there, we are going to call it allyl alcohol. If halogen is there, we are going to call it allyl halide. In the same manner, any of the position of the benzene, any of these positions, these are called phenylic position. While this position, that is the position of the carbon attached to benzene, is termed as the benzylic position. Clear? The group attached to the carbon containing the double bond is termed as a vinylic group. On the other hand, the group attached to the carbon attached to the double bonded carbon is termed as the allylic group. A group attached to benzene ring directly is called the phenylic group, and if it is OH, it's termed as phenol. And the group attached to the carbon attached to the benzene ring is termed as the benzylic group. Now, There could be a direct question to you, like they could give you the compounds, various compounds, and ask them which of these are vinylic compounds, which of these are benzylic compounds, which of these are allylic compounds. Of course, that question could be asked. Then another question could also be asked that which of these is more reactive? Now, you need to understand that if we talk about the double bonded carbon, whether it be in benzene ring or whether it be in the normal aliphatic compound, this particular carbon is sp2 hybridized. Being sp2 hybridized, the rebonding bond strength of this particular carbon is greater than the carbon which is sp3 hybridized. So the hydrogen attached to the vinylic position is less reactive. And in most of the reactions, this particular hydrogen is not at all replaced. Similarly, this phenylic hydrogen also becomes less reactive. And if we talk about the free radical halogenation reaction, the phenylic hydrogen and vinylic hydrogen are not replaced at all. On the other hand, the allylic and benzylic hydrogens are very reactive. The reason for this particular position to be very reactive is very simple. The allylic or benzylic radical, when they are formed, these are conjugation stabilized. Conjugation stabilized. Why is it conjugation stabilized? The simple reason is that if we talk about the vinylic or allylic positions, we have a double bond, we have a single bond, and we have an unpaired electron. And this is one of the conditions of conjugation. The double bond, single bond, unpaired electron becomes the condition of conjugation. So allylic and benzylic radicals are conjugation stabilized. Hence, they are easier to form even than the tertiary radicals. So if we have allylic and benzylic position in a free radical halogenation reaction, so we can rest assured that allylic and benzylic products would be the major product. When we talk about the alkenes, such as we have the allylic or benzylic hydrogen, and we react with certain specific reagents, like we have X2 in presence of light or heat. Now, this X2 could be Cl2, that could be Br2. Generally, we avoid I2 and we generally do not use fluorine. Fluorine is extremely reactive, so fluorine is never used. Or we could have a specific reagent that is NBS. Now, NBS stands for N bromo succinimide, having the structures CH2, CH2, C double bond O, C double bond O, NBR. Generally, it is not written in such an elaborate way. It's simply written like this. We have NBR here, double bond O, double bond O. This is N-bromosuccinimide. In this case, what we find is that it is extremely easy for this NBR bond to break, which leads to the formation of N radical and Br radical, which is able to replace the hydrogen with Br. So this NBS is used in this case. Another compound which we have is called SO2Cl2. Now this is called sulfuryl chloride. The sulfuryl chloride, and you need to be very clear about one simple fact that there is a compound called SOCl2 also. Now this SOCl2 is called thionyl chloride. SOCl2 is called thionyl chloride, and this thionyl chloride and sulfuryl chloride, they behave in a very different manner. Now NBS in presence of light, SO2Cl2 in presence of light. Now SOCl2 is going to give us chlorine radical while NBS gives us a bromine radical. So if we have reaction of X2 with NBS SOCl2, then in that case, what we find is these particular reagents are specifically going to replace the allylic hydrogen. If we have allyl group That is, we have allylic hydrogen. This hydrogen is going to replace by X. If it is X2H nu with light or heat, then in that case we are going to get bromine or chlorine. If we have NBS with light, then in that case we are going to end up with bromine. And if we have SO2Cl2 with light, we are going to end up with chlorine. So same is going to be with the case of the benzylic group. So here we are again going to end up with an X. So this is one method of preparation of haloalkane from alkenes by replacement of allylic or benzylic hydrogen with halogen in free radical substitution reaction. Now we are going to talk about a specific reaction of alkene, and that is what we have as an hydrohalogenation reaction. Now, in case of hydrohalogenation reaction, this is an addition reaction in which the double bond is replaced by the hydrogen and halogen. So this is what we call as hydrohalogenation reaction. It is an addition reaction in which the double bond is consumed. So what we can have is we can have an alkene. We react it with HX. Now this HX could be HCl, it could be HBr, it could be HI. And we end up with the alkene having the double bond replaced by hydrogen and halogen. So this is an addition reaction in which the double bond is consumed to give haloalkane. Now this particular reaction can actually go in two particular mechanisms. Now let's talk about the first mechanism. The first mechanism in which we react the alkene with HX, and that is the concentrated HX. Concentrated HX would mean that it would contain a small amount of water, and obviously small amount or large amount of water. Water is present in this particular reaction. If HX is reacted in presence of water, then in this case the HX is going to dissociate or ionize to form H plus and X minus. Now the question arises that we have H plus and X minus. Which of these species is going to react with alkene the first? Now, we have again to understand that when we talk about an alkene, the alkene contains the carbon-carbon bond having an electron cloud above and below the plane. So any species, if it is going to attack on the carbon, it is not going to actually attack on the carbon, the nucleus of the carbon, but it will have to attack on the electron cloud. This would make the alkenes electron rich, allowing only the electron deficient species, that is, the electrophiles or radicals, to attack on the alkene. You need to understand again that electrophile and radicals both are electron deficient species. Electrophiles because they have an empty orbital or they have a capacity to create an empty orbital, and radicals because they have an unpaired electron, which again would be counted as a deficiency. So electrophiles and radicals both have a capacity to attack on alkene and initiate the reaction. Be very clear that the reaction would be initiated by electrophile or a radical. It is not that the nucleophiles cannot attack on the second instance. Nucleophiles can attack on the second instance, but the first reaction would be of electrophile or a radical. So when we have H plus and X minus, this H plus has the capacity to attack on the double bond. Hydrogen has a valency of 1 and it is not capable of expanding that valency by any means. So hydrogen is going to react and attach to one of these double bonded carbons. So we could have the position like hydrogen is going to attach to this particular carbon. Now the charge has to be conserved. The hydrogen, if it attaches to the one of the carbon, then in that case the positive charge would be created on the carbon adjacent to it. The positive charge is not going to be created on the carbon on which the hydrogen attacks. It will be created on the carbon adjacent to the carbon on which hydrogen attaches. Now, it is not necessary that it's going to be attacking on the left carbon. It could be attacking on the right carbon as well. Now here, this is the case. We don't know whether this particular alkene is symmetric alkene or unsymmetric alkene. As such, the symmetric alkene is the one in which if we identify the main chain and we number it from either of the ends, that is from the left side or the right side, top side or the bottom side, and we get the same name, that is termed as a symmetric alkene. While if we are getting the different name, then in that case it will be termed as an unsymmetric alkene. In case of symmetric alkene, whichever position the hydrogen attaches to, we are going to get the same carbocation. But if it happens to be the different alkene, that is, it is unsymmetric alkene, then in that case, these two are going to be different carbocations. If we have different carbocations, then in that case, the stability of the carbocation is going to differ. So the carbocations are going to have different stability in the case of unsymmetric alkene. Now, what we need to do is when we have an alkene, which would give us a different carbocations, so we have to find out the relative stability of the carbocations. Now, there's a very simple thing. If in a reaction, if a reaction can proceed through more than one different intermediates, carbocation, carboanion, radicals, these are intermediate of the reaction. A reaction which can proceed through more than one different intermediates, then the major product is obtained from the more stable intermediate. That would simply mean that if we have two different carbocations which are being formed, then the more stable carbocation would be more easily formed. It will be the major thing in the reaction mixture. And so, obviously, when the product is formed, the major product would be formed from more stable carbocation. So here, this particular carbocation and this particular carbocation are going to react with X minus present in this reaction mixture, and we are going to get the hydrogen here, the halogen here. Here it is not a necessity that we have to put the halogen on the top that is diagonally opposite to the hydrogen. It could be from on the same side, it could be on the different side. And further, it actually doesn't make a difference because there is a single bond which can always rotate to get the hydrogen on the same side of the halogen or the opposite side of the halogen. So it is not a same side attack, which is termed as a syn attack, and it is also not the anti attack, that is the opposite side attack. Syn and anti means same side and opposite side of the bond. So this is a simple reaction in which we are going to get the alkyl halide or haloalkane. Let's have a few reactions. Like we have the first thing, we can react CH2, double bond CH2 in with concentrated HBr. We could take HCl also. We could take the HI also. So let's take in the case of concentrated HBr, we can have CH2 reacting with concentrated HBr. Then we could have something like CH3, CH, double bond CH, CH3. Then we could have something like CH3, CH, double bond CH, single bond benzene ring. Then we could have something like CH3, CH, double bond CH2, and we could have something like CH3C, CH3, double bond CH, CH3. Now you could pause the video at this point and you can attempt these questions, or you can just go on with the answers here. When we talk about the CH2 reacting with HBr, we have H plus and we have Br minus. Obviously, the H plus is going to react the first because this is an electrophile. It could react on the left carbon or the right carbon. If it attacks on the left carbon, we are going to get CH2. Here we are going to have hydrogen, and the positive charge is going to be on the right carbon. And if it attacks on the right carbon, then in that case, we are going to have CH2, CH2 having the H on the right carbon and the positive charge on the left carbon. So we are going to get these two carbocations. Since CH2, CH2 is an asymmetric alkene, that is why both the carbocations are the same. So here, these are the same carbocation, and then we can have the Br minus attacking it. If the Br minus is attacking it, then in that case, we are going to get only one product. Since both the carbocations are exactly the same, so we are going to get CH2, CH2Br, that is bromoethane or ethyl bromide in the common terms. In the second case, we are again going to have the hydrogen attacking on the left carbon of the double bond or the right carbon of the double bond. If the hydrogen attaches to the left carbon of the double bond, then in that case, here we have hydrogen and here we have the positive charge on the right carbon. Again, we are going to have another carbocation. We are going to have CH, CH. Here it is CH3 and here it is H, the positive charge on the left carbon. Again, you can understand that but2ene turns out to be a symmetric alkene. Since it's a symmetric alkene, both the carbocations are exactly identical. Being identical, again, we are going to get only one product here, where it is CH3, CH2, CH, CH3, and here we are going to get bromine. That is 2-bromobutane would be the only product that we obtain in this case. So these are the two symmetric alkenes where the reaction gives only one product. On the other hand, we talk about this particular reaction. Here we can get the alkene CH3, CH, CH, the benzene ring. Now we have the hydrogen attaching to the left carbon. The positive charge is going to be on the right carbon. And another thing, we have CH3, CH, CH, the benzene ring. The hydrogen attaches on the right carbon and the positive charge is on the left carbon. Now, as you can very well see, these two carbocations are not identical. Of course, the stability of these two carbocations also is not going to be the same. It is going to have a different stability. If we talk about this particular carbocation, the first carbocation, here the stability of the carbocation is decided by mainly three factors. The first factor is either if it is aromatic or not. Second factor, if it is conjugated or not. The third factor, if it is hyperconjugated or not. And there is even a fourth factor, which could be called as inductive effect. The plus I effect stabilizes the carbocation, that is, electron pushing groups stabilize the carbocation. Now, in this case, if we consider here, the carbocation is not aromatic since it's not the part of any aromatic ring, but the first carbocation is conjugated. That is, here we are satisfying another condition of conjugation. That is, we have a double bond, we have a single bond, and we have an empty orbital. The benzene ring contains the double bond, there is a single bond, and this carbocation contains an empty orbital. So first carbocation is conjugated. In addition to being conjugated, the carbon attached to the carbon containing the positive charge, this is the alpha carbon. The alpha carbon contains two hydrogens. So here we have two alpha hydrogen as well. And these alpha hydrogen have a capacity to hyperconjugate. So here we have two alpha hydrogen hyperconjugating, and this particular carbocation is also conjugated. On the other hand, if we talk about the second carbocation, there is no conjugation here. But again, it is hyperconjugated. We have two alpha carbons. Remember, all the carbons attached to the carbon containing the positive charge are termed as alpha carbons, and all the hydrogen attached to the alpha carbons are alpha hydrogens. So it contains five alpha hydrogen to hyperconjugate. If we were talking about hyperconjugation alone, then the second carbocation would have been more stable. But we are talking about conjugation also in the first carbocation, and conjugation dominates over hyperconjugation. So the first carbocation is more stable. Now, these are going to react with the Br minus, and we are going to get the two products. Like here in this case, we are going to get CH3, CH, H. CHBr, the benzene ring. In this case, we are going to get CH3, CH, here it is Br, CH, and benzene ring. Now, as I have told you, the major product is formed from the more stable intermediate. In this case, more stable carbocation. So, more stable carbocation being the first one, this would be the major product, while this would be the minor product. So, this is what happens when we have unsymmetric alkene. We have to talk about the stability of the carbocations which are being formed. Considering the next reaction, here again we are going to get the two carbocations. Again, this is an unsymmetric alkene, so we are going to get two carbocations. This is going to be the one carbocation CH3CH, and here we have H, here we have CH2 and positive charge, and then we have CH3CH, CH2. Here we are going to get H, and here it is the positive charge. Now, in this particular carbocation, when we check these two carbocations, there is no aromaticity, there is no conjugation, but there is hyperconjugation. This is the alpha carbon in this case, and there are two alpha hydrogen to hyperconjugate. While in the second carbocation, this is the alpha carbon, this is the alpha carbon, and we can actually count six alpha hydrogens to hyperconjugate. There isn't any confusion, and you can simply say that the second carbocation is more stable as compared to the first carbocation because the second carbocation has more hydrogens to hyperconjugate. So when we react it with the Br minus, we are going to get two products as is understood. This one would be the product CH3, CH2, CH2Br, and this is going to be CH3, CH, CH3Br, and this would be the major product because it is formed from the more stable carbocation. Let's talk about the fifth reaction, fifth compound. Here we have CH3C double bond, no, now it becomes a single bond because we are going to convert it into carbocation. CH3, here we have CH3, and if we add hydrogen here, this is going to become the carbocation. If we had the hydrogen on the other side, CH3, C, CH3, CH, hydrogen added here, CH3, this is going to be the positive charge. Again, there is no aromaticity here. There is no conjugation here, but there is hyperconjugation. If we consider this particular compound, then this is going to be the alpha carbon, and this is going to be the alpha carbon. So total alpha hydrogen that we have, there are four alpha hydrogens in this particular carbocation. While if we talk about this particular carbocation, the other carbocation, this is going to be alpha, this is going to be alpha, and this also is alpha. So in total, there are eight alpha hydrogens. So there is no contest, and this one is more stable. Considering this to be more stable, we find that if we react it with Br minus here, we react this one with Br minus here. Here we are going to get the compound as CH3, CH, CH3, CH, Br, CH3, and here we are going to get CH3, C, CH3, CH2, CH3, Br, and this would be the major compound because it is formed from the more stable carbocation. So this is the reaction that we get, and this is the hydrohalogenation in presence of concentrated HX. This reaction follows a carbocation mechanism wherein the H plus attacks first, forming a carbocation. If we have unsymmetric alkene, then the two different carbocation would be formed. One would be the major one, which is more stable. The other would be the minor one, which is less stable. The major product would be formed from the more stable carbocation. So this is the summary of this particular reaction. Now we talk about another reaction. And now we talk about something called the organic peroxides. The organic peroxide can be termed as something like we have alkyl group with oxygen single bond. The other group could be anything. It could be hydrogen. It could be another alkyl group. So this is one organic peroxide. Another organic peroxide could be where we have acyl group. Acyl group means RC double bond O followed by OO. Now these are the acyl groups. These are the alkyl groups. Now, when we have these acyl and alkyl groups and we have organic peroxide, these organic peroxide in presence of light actually dissociate, breaking the oxygen-oxygen single bond. When they breaking the oxygen-oxygen single bond, the alkyl peroxide would turn to give RO radical, while the acyl peroxide are going to form RC double bond O radical, which is going to further release carbon dioxide to form R radical. Now we could have R radical or we could have RO radical. The various organic peroxide that we could have, the examples could be CH3OOCH3, that is dimethyl peroxide. We could have something like CH3C double bond OOOH. This is peracetic acid. We could have CF3 C1, 2, 3 oxygen. Remember, if we have three oxygen, this turns out to be a peroxide H. This is perfluoroacetic acid. We could have benzene ring with C double bond O, 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 H per benzoic acid. We could have benzene ring with C double bond O, 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 C double bond O with the benzene ring again. This is benzoyl peroxide. Now, these all are peroxides. These peroxides are capable of giving radicals. Remember, this is a radical. This also is a radical. So, these peroxides are capable of providing radical in the reaction. Now, how do these radicals help? Let us say we have a radical, which could be R radical, which could be RO radical, and we react each of them, any of them, with HBr. Now you need to remember this reaction proceeds only with HBr and it does not work with HCl or HI. In case of HCl, the R radical or RO radical will not be able to break the HCl bond, and in case of HI, if we are able to break the HI bond and it is easy to break, the I radical is much less reactive to initiate the reaction. So this particular reaction does not work with HCl, this does not work with HI, it only works with HBr. So here we have R radical. Now you can now here it is again a very important fact that the carbon hydrogen bond is stronger than hydrogen bromine bond, while carbon bromine bond is weaker than than hydrogen bromine bond. Similarly, oxygen hydrogen bond is stronger than hydrogen bromine bond, while oxygen bromine bond is weaker than hydrogen bromine bond. So it is very obvious that if the R radical attacks on hydrogen, or RO radical attacks on hydrogen, the reaction will take place. If they happen to attack on bromine, the reaction will not take place. So what we find is this R radical attacks on hydrogen, the bond cleaves, a bromine radical is released out, or this bromine radical which is going to be formed. This is the reaction initiator. This is going to attack over here. The bond cleaves, the bromine radical is formed. We are going to get RH plus bromine radical. Here we are going to get ROH plus bromine radical. Now this bromine radical has a capacity to attack on the alkene. So this is the reaction initiator. We have an alkene and this alkene reacts with bromine radical. When this reacts with bromine radical, you have to see that bromine radical again is an electron deficient species. This has a capacity to attack on alkene. So if it can attack on alkene, let us say that bromine radical reacts on the right carbon. We have bromine here. The radical will be produced on the left carbon. The carbon on which the radical attacks, the carbon adjacent to it gets the radical. And if it happens to attack on the left carbon, then the radical would be produced on the right carbon of the double bond. If it is again a symmetric alkene, then in that case, both the radicals are going to be identical. But if it is unsymmetric alkene, the radicals are not going to be identical. And as with the carbocation, we need to talk about the stability of the radicals as well. The more stable radical would be more easily formed, and therefore it turns out to be the major product. Now, these radicals can further react with HBr. Now, the radical, again, we talk about, it is going to have the reaction taking place on hydrogen because, again, as we have talked about the logic, that hydrogen bromine bond is stronger than carbon bromine bond but weaker than carbon hydrogen bond. So, this radical is going to attack on hydrogen. The radical is going to attack on hydrogen. The bond again is going to cleave. We are going to get the bromine radical, which is going to carry the chain further. So here the reaction requires the peroxide only to initiate the reaction, not to carry it further. The bromine radical formed in the reaction will be enough to carry the reaction further. So small amount of peroxide is required to initiate the reaction, and we are going to get C, C. And here we are going to get hydrogen here while bromine is here. In this case, we are going to get carbon, carbon, and here we have the bromine and we have the hydrogen here. So this is what we're going to get, the haloalkane, the bromide. If the symmetric alkene is there, only one product is obtained. If unsymmetric alkene is there, two products are obtained, and the major product is formed from the more stable radical. Now, this particular reaction following the radical mechanism is called the peroxide effect. And this was proposed by Professor Kharash. I don't know whether it is Kharash or Karish, but it is also called the Kharash effect. As you can very well see, this reaction follows a different mechanism than the previous reaction. This is hydrohalogenation, no doubt to that hydrogen and halogen are being attached to the double bond, but this is following a radical mechanism while the previous reaction was a carbocation mechanism. So again, we are going to have the same reactant as before. That is, we have the reaction with CH2, double bond CH2. We have the reaction with the CH3, CH, double bond CH, CH3. We talk about the reaction with the CH3, CH, double bond CH, benzene ring. And we talk about the reaction with the CH3, CH, double bond CH2. And we talk about the reaction with the CH3, CH3, double bond CH, CH3. As before, you could pause the reaction here, the video here, and you can attempt these questions on your own, or you can continue with the answers. So here we are going to talk about the reaction with the bromine radical, like we talk about HBr in presence of peroxide. The reaction is going to initiate by the attack of the bromine radical. The bromine radical is going to react with any of these two hydrogen carbons. Now let's say we consider that bromine attacks on the right carbon. The radical would be formed on the left carbon. If it attacks on the left carbon, the radical is going to form on the right carbon. As we can very well see, this is a symmetric alkene. So being a symmetric alkene, both the radicals are absolutely identical. The radical being absolutely identical, it is going to give only one product. So when HBr reacts with it, the hydrogen is going to attach to the radical, consuming it. We are going to get CH2. We are having CH2. We are having Br, and we are going to have hydrogen. So again, we are going to get CH3, CH2Br, that is bromoethane or ethyl bromide as the only product. Here again, we are going to react it with Br radical, that is HBr in presence of peroxide. We are going to get CH3, CH, CH, CH3, allowing the Br to react on the right carbon. We are going to have bromine here. We are going to have radical here. Again, we are having CH3, CH, CH, CH3. The bromine is attacking on this particular position. The radical is going to be formed on the right carbon. Again, this is a symmetric alkene, so we are going to get only one radical. If we are getting only one radical, we are getting only one product. That is CH3, CH, CH, CH3. One of the hydrocarbon gets hydrogen, another carbon gets bromine, and we get the product as 2-bromobutane as the only product. Considering this particular reaction, here we have CH3, CH, CH, the benzene ring. If the bromine attacks on the right carbon, Br, the radical is produced on the left carbon. And if bromine attacks on the left carbon, the radical is produced on the right carbon. Now, this is an unsymmetric alkene, so these two radicals are not equally stable. One of the radical is more stable than the other radical. So, what we find here, if we consider the first radical, we do not have conjugation, we do not have aromaticity, but we do have hyperconjugation. This is the alpha carbon, this is the alpha carbon, and we have four alpha hydrogens hyperconjugating here. There are four alpha hydrogens hyperconjugating here. And if we talk about the second one, this is the alpha carbon. There is only one alpha hydrogen hyperconjugating. But here we have the condition of conjugation being satisfied. That is, we have a radical, single bond, and a pi bond. So this is conjugated. Conjugation dominates over hyperconjugation and find that this particular radical is more stable. Now it reacts with HBr, the hydrogen attaches with it, the HBr is reacting going to it, and we are going to get the product as CH3, CH, benzene ring. Here we have Br and here we have hydrogen. The other product is going to be CH3, CH, benzene ring. Here we have Br and here we have hydrogen. The second product is being formed from the more stable radical, so this turns out to be the major product. Considering propene, we have CH3, CH2. If bromine is to attack on the right carbon, we get the radical on the left carbon, and we have CH3, CH2. Bromine attacks on the left carbon, we get the radical on the right carbon. Considering the stability, here there is no conjugation, there is no hyperconjugation, there is no aromaticity, but there is hyperconjugation. These are the alpha carbons here. Here we have three carbons on the left side and the two hydrogens on the right side, three hydrogen on the left side. So there are total five alpha hydrogen. In this particular case, we have this one as the alpha carbon. Please remember the carbon attached to the alpha carbon is not alpha, it is beta. So we are talking about alpha hydrogen. So this is going to be only one alpha hydrogen in this case. So is it not very obvious? This is going to be more stable. Now they are going to react with HBr. When they react with HBr, it's going to be CH3, CH, CH2, Br here, H here. This is going to be CH3, CH, Br, CH2, Br here, and this is going to be the major product since it is being formed from the more stable radical. Similarly, let's talk about this particular reaction. Reacting with HBr in presence of peroxide, we get it CH3C double bond, single bond now. CH3. Here we have CH3, and let's say we have the bromine attacking on the right side. The radical is going to be formed on the left side. And if bromine happens to attack on the left side, the radical would be formed on the right side. Now let's talk about the stability of these radicals. Here, if we talk about this particular, this is alpha, this one is alpha, this one is alpha. So we have seven alpha hydrogens in this first case. And if we talk about this one, this is the alpha, this one is alpha. The left alpha doesn't contain any hydrogen, right alpha contains three hydrogens, so there are three alpha hydrogens. Obviously, this becomes more stable. Being more stable, now these two are going to react with HBr, and we get it CH3, C, CH, CH3. Here it is CH3. Here it's going to be H, and here it's going to be Br. Here we get it CH3, C, CH, CH3, CH3. Here it is Br, and here it is H. Now we find that this one turns out to be the major product. We can summarize the products which are obtained in these reactions, and we can have like we have first one as CH2 double bond CH2. Second one we have as CH3 CH double bond CH CH3. The third one we have as CH3 CH double bond CH benzene ring here. We have fourth one as CH3 CH double bond CH3 2, and we have fifth one as CH3 C CH3 double bond CH CH3. We react with each of them. We react it with concentrated HBr. That is, this is a carbocation mechanism. The carbocation is being formed. In this case, the major product turns out to be CH3CH2Br. Let's say we consider the reaction with HBr. We can talk about in this particular reaction HCl or HI as well. Here the major product is going to be only one CH3CH2 CHCH3Br. But in this case, the major product can be two. There are two possible products. The major product would turn out to be CH3CH2CH benzene ring. Here we are going to get Br. In this case, the major product turns out to be CH3CH, CH3Br. You can look at the mechanism earlier. Here, the major product turns out to be CH3C, CH2, CH3, CH3, and Br. Now, the same reaction taking place in presence of HBr, peroxide, non-aqueous medium. Now, this is what we call as peroxide effect or Kharash effect, and this is a radical mechanism. This is a radical mechanism. So here the major product turns out to be the only product turns out to be CH3CH2Br. Here the only product turns out to be CH3CH2, CH, CH3Br. Here the only product is CH3CH2. Here we are going to get two products, but the major product turns out to be CH3CH, CH2 benzene ring, and here it is Br. So first and second compound are the same, whether the mechanism is a radical mechanism or carbocation mechanism, since they are symmetric alkene, doesn't make a difference. But in the third case, the major product is different in the two mechanisms. And in this case, CH3, CH2, CH2, Br would be formed. And here it is going to be CH3, CH, CH3, CH, Br, CH3 would be formed. So these are the major products in these five reactions. As you can see, the first and second would give the same product, third, fourth, fifth give different products because the mechanism is different. Now we have a very simple statement. In case of fourth and fifth, we find that the carbon containing the double bond have different number of hydrogen. So In case of unsymmetric alkenes, in case of unsymmetric alkenes having different number of carbons, number of hydrogen, number of hydrogen on the carbons of double bond. On the carbons of the double bond. If in the addition reaction the hydrogen attaches to the carbon of the double bond which already has more hydrogens, that is rich, becomes richer, then it is termed as Markovnikov's addition. And if the hydrogen attaches to the carbon of the double bond which has less number of hydrogen, that is poor becomes rich, it is termed as anti-Markovnikov addition. Please remember there isn't anything called Markovnikov rule or anti-Markovnikov rule. You have to do the reaction according to the mechanism, and then if the two carbons have different number of hydrogen, then you can consider one of them to be the Markovnikov addition or another one to be the anti-Markovnikov addition. But the Markovnikov addition and anti-Markovnikov addition have to be determined after looking at the product and not predicted by Markovnikov or anti-Markovnikov. Clear?